Okay, everyone, welcome. Are there any questions people have? Okay. Well then, let's just go right into it. Let's start with a warm-up. Define what a second order homogeneous constant coefficient linear differential equation is. There's a lot of descriptors there. So let's see if we can understand what each term means. Okay, so why don't you work on that, and then also, as another warm-up, solve the initial value problem. Y prime minus ky equals 0, or plus ky equals 0, with y of 0 equals 5. All right, so why don't we work on that for a little bit? Feel free to work together in groups if you'd like. This is normally what I do back in the olden times. You can now maybe private chat with someone if you'd like. You can private chat with me, or you can just talk in the whole group to discuss what these warm-up problems. So why don't we work on this a little bit? And then we'll go over it. Also a reminder, regrade requests close, I think tonight, so at 7. According to Nikhil's email some time ago, correct me if I'm wrong there though, but so yeah, you should ask either me or another GSI if you have questions on your exam. So hopefully we're all working on this. We'll do it for like a minute or so, just to get our brains working. Okay, so why don't we talk about at least the first one. So a general second order homogeneous constant coefficient linear differential equation looks like this. So what does each term mean? So second order means that there's only two derivatives, at most two derivatives. Homogeneous, oops, means that you're setting the differential equation equal to 0, just like you have when you have a homogeneous linear system, like a homogeneous matrix equation, AX equals 0. We're setting the differential equation equal to 0, so there's no constant term. Constant coefficient means that each one of these A, B's, and C's are constants. Right, they're real numbers. So they could be, so later they could be functions, A of t, B of t, and C of t. But for now, there's going to be real numbers, just constants. That's what constant coefficient means. And linear, let's see, linear means that you don't have things like y prime times y. So there's no like y times y prime or y prime squared, for example. Right. So when we later talk about this in the course, it means if we don't have this, it means we can rewrite this as kind of a matrix equation. Well, I'll leave that. We can linear implies rewrite this as a matrix, which I'll leave for later because we haven't discussed it yet. But if you had like quadratic terms, you wouldn't be able to do that. Okay, so now let's practice solving the initial value problem given here. This is a first order differential equation. We talked a little about how to solve this last time. So this is separable. This is separable. So you can solve it. You can put all the y's on one side. And then non-y's on the other. You can integrate both sides, and you find that the solution is y of t equals some a e to the negative kt. And you can just check it, right? You can just take this, multiply by k, and add the derivative, and you'll get 0. Right? Because the derivative of this with respect to t just brings out a negative k. So this is the general solution. And there's a question, does first order equations have an auxiliary polynomial as well? So the auxiliary polynomial is where you kind of plug in r, or, e to the rt, and you plug it in here. Yeah, I guess so. Because if I were to do that, then I would get r plus k equals 0. Just instead of a quadratic, it's a it's a linear polynomial, and so you get r equals negative k, and then you plug that back in. So yeah, you can do the same thing. And then now we have this initial value problem. So we'll talk about auxiliary polynomials again right after this as well. We plug in the initial value to get the exact solution, the particular solution. So we plug in 0 and set that equal to 5, and we find that a equals 5. So I'll write it here. Hopefully you can see that. Y of t equals 5 e to the negative kt. This is the particular solution. K was just a given constant. We're not solving for K. K is just given. Are there any questions on the warm-up? Okay, then in that case, let's kind of review and talk about second order differential equations. So we're given, we want to solve a y double prime plus by prime plus cy equals 0. This is kind of the first differential equation we're going to solve. for second order differential equation, and then we'll adapt these solutions to non-homogeneous equations and then nth order equations and so forth, and equations where they don't have constant coefficients. Right, but the first thing, which we talked a little about with on Wednesday, which is we can rephrase this more linear algebraically. And we want to connect it to the last 4 months of what we've learned. To do that, we need to introduce a vector space and a linear transformation of that vector space. So the vector space we're going to consider is the vector space of what it's called smooth functions. So smooth here from R to R. Smooth means infinitely differentiable for us. So this means infinitely differentiable. Which you can kind of imagine like an infinitely differentiable function means there's no like sharp points. There's no like undefined derivatives, but moreover, there's no undefined second derivatives, third derivatives. So like if you were to try to draw it, you kind of would imagine drawing a very like just a smooth function. Like there's no sharp points. That's kind of what smooth means. Okay, and our differential operator, our linear transformation, is going to be just the derivative function. D is going to be, we're going to define D by, well, actually, maybe we should define maybe little d by D is going to take a function and it's going to output the derivative of that function. And then we can define big D to be the second order differential equation. So it's going to be a little d squared plus b d plus c. So what this means is d squared, for example, means like first you apply, it's like d composed d is really what I mean by this. So you take d, you apply it to a function, then you apply it again. So that's going to give you the second derivative. And what I mean by here, this is addition of linear, this is addition of linear transformations. And I guess what I mean here is you have the identity linear transformation. So we've kind of seen this a little before when we talked about transformations between like polynomial spaces, for example. But I mean, just to reiterate this, what I mean is if D takes a function f and it outputs a d squared f dt squared plus b df dt plus cf. Right, so it's exactly this differential equation. Right, and so maybe just to refresh ourselves, let's just check D is in fact is linear. It's a linear transformation. Right, to do that, we need to check two things, which we've done before. We need to check that D applied to an addition, the sum of two functions, should be the sum of the outputs. And we need to check that it respects scalar multiplication. I won't use C because we already have a C. D of lambda f. So we need to check these two properties. And these two are just, the proof is essentially the same. It's just because derivatives are linear. It's just because if you take a times d squared over dt squared of a sum of functions, it's just going to distribute. That's just how derivatives work. This is going to equal, you can break it up. And so forth. So you're going to get exactly what you need to get. So D is a linear transformation. We've seen this a little before, again, between polynomial spaces. And the point of all this is that if we want to, what's the input for little d? So this D is a linear transformation here. And it takes in a function and it outputs. So maybe this is maybe a little confusing because d by dt is a well-known symbol for differentiation. And this little d here is just a symbol I'm using for a transformation. So this is a linear transformation. And it takes in a function. Like maybe I'll call this, maybe so that we don't get confused, let's call this something else, t. And now, yeah, now everything's well defined. Okay, so the takeaway of all this is that we want to solve this differential equation up here, right? And that differential equation is encapsulated by this linear transformation. So what we want to do, I'm going to go to another page, solving a y prime double prime plus b y prime plus c equals 0 is finding polynomials, not polynomials, functions. Finding functions in V that satisfy what? Well, they satisfy d of y equals 0. Functions y in V. Right, because d is exactly this differential equation, i.e. finding the kernel of d. Right, so solving a differential equation is exactly finding the kernel of a linear transformation. And this is something we're well practiced in. We know how to find kernels of linear transformations. Well, we do when the linear transformation goes from a finite dimensional vector space to a finite dimensional vector space, because then we can rewrite the linear transformation as a matrix. We can find a basis for the null space of the matrix and can convert that back to the vector space and so forth. But this is a little more tricky because V is the infinite dimensional vector space. So we're gonna maybe gloss over a few things. So one, we have this fact, which is that since star is a second order differential equation, kernel of D is a two-dimensional subspace inside V. We might talk about this a little later, but for now, let's take this for granted that since we have a second order differential equation, that the kernel is two-dimensional, which means all solutions to star are some linear combination of just two solutions. Those two solutions will be two linearly independent solutions. There'll be a basis of the kernel of D. So all solutions are some linear combination of just two linearly independent solutions. Let's say y1 of t and y2 of t. these will be a basis of kernel of D. And so if we want to solve star this differential equation, all we need to do is find two linearly independent solutions, and everything else will be a linear combination of them. So that's our goal. Our goal is to find two solutions, two linearly independent solutions. We'll talk a little later about what it means to be linearly independent as functions. But for now, let's just get into the details about how do we actually solve this differential equation? How do we find these two linearly independent solutions? How to do this? Okay, and maybe let's just do it with an example. Okay, so how do we find solutions? So basically, I mean, there is theory behind all this, but we're not going to go too much into the theory of differential equations. Basically, what you're going to do when you solve a differential equation is you're going to guess. You're going to guess a solution, and you're going to plug it in, and then you're going to see what it needs to satisfy the differential equation. So otherwise known as guess and check. Because fortunately, people have done this before, and they know solutions. And so one thing we know to guess is this e to the RT. And then you plug it in, and you see what R needs to be, and those are your solutions. So we plug it in, we get R squared e to the RT minus 5 R e to the RT plus 6 e to the RT equals 0. I'm just plugging in y into this differential equation, and I get this equation, and we call this the auxiliary polynomial, I guess, or otherwise also the characteristic equation, because it's very similar to diagonalizing, what we'll see later, but we call it the same reason, or the same name as when we diagonalize. It's not too important when we actually call this, but the point is, if you want to solve this, you want to find roots of this polynomial, because e to the RT here, this is never 0, which means if this product equals 0, it means this polynomial has to equal 0. So R squared minus 5R plus 6 equals 0. So we find roots of this polynomial. R minus 3, R minus 2. So we get R equals 3 and 2, from which we find two solutions. E to the 3t and e to the 2t. And these are two different solutions. And in fact, they're linearly independent, which we'll find out later. So we find that all solutions are of the form C1 e to the 3t plus C2 e to the 2t. Right? Because all solutions are just linear combinations of these two solutions. So this we call the general form. Maybe this is a general solution, because all solutions are of this form. And if you want a particular solution, then, so if I give you also some initial values, if I give you y of 0 equals something, and y prime of 0 equals something, or y prime, I mean, it doesn't have to be 0, it could be any number, but if I give you what they are, then you can plug it in here and you can figure out what these constants need to be, And whatever you figure out, that's your particular solution to the initial value problem. So it's actually not too hard to solve these. You basically just reduce it down to finding roots of this characteristic equation, or this auxiliary polynomial. So this is an easy example, though, because what happens when these polynomials, this r squared minus 5r plus 6, what happens if it doesn't have two distinct roots? Or what if happens if the roots are complex? And so we change our answer a little. And we have this kind of this table. So we have ay double prime plus by prime plus c equals 0. We get ar squared plus br plus c equals 0. And we see that if there are two distinct roots, then you get two linearly, let's call them R1 and R2. Then you get two linearly independent functions that are solutions. E to the R1t and e to the R2t. If you have a double root, R, then you have two linearly independent solutions, e to the RT, but you also have this other solution, which you just multiply by an extra power of t. Why you do that is maybe a little mysterious at this point, but that's just what you do to get another linearly independent solution. We will maybe we'll generalize this to nth order differential equations, and maybe we'll see a little about why you get this t. But for now, we kind of just do this, and then we get a, let's say we have two complex roots. Let's say real. These are, in this case, the roots are real. Two complex roots, R1 and R2. Let's say R1 equals alpha plus beta I, and R2 will have to be the complex conjugate because these are real. A, B, and C are real. Then you get two linearly independent solutions, and you can write them the same way. You can do y1 of t equals e to the r1 of t, and y2 of t equals e to the r2 of t, where r1 and r2 are now complex numbers. But there's maybe a better way to write this because these functions are not, well, they're not real valued, I guess. And so you kind of want, if you want a real function that describes your solution, what you want to do is kind of rewrite them as two linearly independent real valued functions. And so you can write them as such. You get e to the alpha sine beta of t, and or if you want, I'll keep with my notes. Cosine beta of t doesn't really matter because you're gonna write both of them. E to the alpha sine beta of t. Oh, sorry, there's a t in here. And so these are real valued on the bottom. And so oftentimes we prefer these ones as two linearly independent solutions. But these are equivalent just because there's a linear combination of these top two that give the bottom two. I'll call these something else. I'll call these y1 hat and y2 hat. Equivalent because y1 hat plus y2 hat over 2 equals y1. So there's a certain linear combination that gives you y1. All right, so the span of the bottom two is going to be the same as the span of the top two. We're just picking a different basis. And y1 minus y2 over 2 I will be y2. Okay, so this is kind of the table you just maybe should know for now. And this will help you solve differential equations. So the best way to do it, or to learn, is just to do some practice problems. So there's some problems on the worksheet, which I'll write on here, which is solve the following, where it says find general solutions. Y double prime there's another one, and then find particular solutions for some of them. So why don't we work on some of these for a little bit? So yeah, we can work on these for a little bit. You feel free to ask me any questions, then we can go over them. And that's mostly what I wanted to go over today. But you're welcome to venture into other territory. Again, you can find these on my worksheet. On my website. I think for the first one, you get the general solution is C1 e to the wait, oh, that's kind of annoying. Okay, whatever those roots are. For some reason, I gave a polynomial that you have to use a quadratic formula for. Okay, let's see the second one. I probably just took these from the book, to be honest. I guess it is a quadratic formula for both of these. I don't know, anyone finding some solutions? Or does anyone want to talk about some of these? Got 1/2 of the second one. Yeah, the second one, let's see. Yeah, I think 1/2 works. You get +4th. Yeah, 1/2. As a double root. So you get e to the 1/2 t as one solution, plus your other solution is the same thing, but you have this extra t floating around. And this has just some radicals in it. So yeah, solving differential equations isn't too difficult, I guess, once you just basically just boil, at least for the second order differential equations, it just boils down to finding roots of a quadratic. And then if you want a particular solution, you then need to solve for these constants. So maybe, I mean, there's not much more to say. On Monday, we'll go over more in depth as well. But maybe we can just end early today. But I'll stay on for a while longer if we want to talk about differential equations. So I'm going to end the recording there.